Welcome to Signal Science System subject classes. The Signal Science System subject is a fundamental and a basic subject for electronics and electrical engineering as well as electronics and telecommunication. So subject is very important for the communication systems and control systems. The communication system and control system, signal processing and DSP subjects, these are developed on the signal science system subject. Coming to the gate examination. So in gate exam and engineering service examination, which is being conducted by the UPSC, Union Public Service Commission. So these two are included this subject into their syllabus. And also every state public service commissions in their examination, they included the signal science system in engineering service examinations. And power sector exam also included the signal science system. So signal science system is one of the important subject all these 4 competitive examinations. Is it? Coming to the syllabus. In first chapter, in this basic, in first chapter in this signal science system subject, we will discuss basics of the signal science system. So in this chapter, we will discuss about definition of the signals and signal representation, how to represent the signals, how many ways we can represent the signal, and types of the signals, impulse signal or unit step ramp signal. There are so many signals are there. And also we will discuss the periodic signals and aperiodic signal, their characteristics. In the end of this subject, we will discuss also the definition of the system and system properties, like we will test whether it is a memory system or memoryless system, and its causality, whether it is causal or non-causal. Stability also we will find, and we will focus checking its invertibility, and also we will know how to find the linearity and time invariant properties. So these are the properties of the system. So all these things will be discussed in the first chapter. So in first chapter, we will know that signal representation. So the signal representations are 2. First one is continuous time. The second representation is discrete time. Is it? Continuous time signal and discrete time signal. Any signal can be represented in 2 ways. One is continuous time signal, and the second one is discrete time signal. Then next chapter, we will go for the discussing the LTA system. LTA means which system it follows default linearity and time invariant properties. The system said to be LTA system. So here, so in the chapter, so we will discuss continuous time LTA system LTE system, as well as discrete time LTE system. Is it? So here the important thing is we will learn how to find what is the convolution. It's a very convolution. We will learn about convolution. So convolution. Especially in this chapter, we will learn to find convolution with the help of graphical method. This is a very important. In graphical method, we will find the convolution of the system in between two signals, or signal and system transfer function or impulse response. In third chapter, now in third chapter we are going for the conversion. So here the conversion, what is the conversion? Now our intention is converting time domain signal to the frequency domain signal, as well as frequency domain to the time domain. T to F, it is a forward transformation. If F to T, it is called inverse transform. So in the first case, this technique, the technique which is used for the converting the time domain to frequency to time domain, the first technique, it is called Fourier series. Fourier series. So this Fourier series, it is for, you should remember, this Fourier series, it is for conversion from the time to frequency, so frequency to time domain. Is it? So this is a fundamental concept. So remember, the application of the Fourier series is converting time to frequency to time. So here also already signal can be represented in two ways, CT and DT. Then for CT we will learn the Fourier series. So that Fourier series called for, in case of CT, that is continuous time Fourier series. And in case of discrete time, that Fourier series called discrete time Fourier series. Means the Fourier series concept, it is applied individually for continuous time and discrete time. So here we have two types of Fourier series. Is it? Then, so next chapter. Again, in next chapter again we are going for learning conversion from time to frequency and frequency to time. Time to frequency and frequency to time. So this technique is called Fourier transform. Then, so these two are converting time to frequency and frequency. Already we have learned the converting method in Fourier series. Then why we are going for the another technique? See, this fundamental you should remember. So very important, the concept. So this Fourier series, it is applicable for only periodic signals only. So only periodic signal only, with the help of Fourier series we can convert time to frequency and frequency to time. So this Fourier series, we can say that the Fourier series, it is not applicable for the aperiodic signal. So that is the main drawback of the Fourier series. That's why we are going to next technique, that is Fourier transform. So this Fourier transform, it is applicable for the aperiodic signals. Is it? Aperiodic signal. As well as this Fourier transform, it is applicable for periodic also. But the basic thing is, it is mainly used for the converting time to frequency and frequency to time for especially aperiodic signals, is it? This Fourier is it's only for the periodic, is it? Here also, in Fourier transform also, for continuous time signals, that Fourier transform is called continuous time Fourier transform, is it? So here also we have two Fourier transforms. One Fourier transform for the continuous time representation, another one discrete time Fourier transform, is it? So there is a major difference between Fourier series and Fourier transform. Then next we are going for the next chapter. We will discuss Laplace transform. So this Laplace transform, so it is also, it's a so Laplace transform, it is also used for the converting time domain to the frequency domain. So here frequency is called S domain. So inverse Laplace form means inverse Laplace transform from S domain to the time domain. So this Laplace transform, it is a modification from the CTFT, is it? So here in CTFT or DTFT, in DTFT, with the help of CTFT and DTFT, we cannot find the stability. That is a major drawback of the Fourier transform. To find the stability, then the CTFT, it is modified to the Laplace transform, is it? So the major reason is stability. So because of the stability, is it? So the CTFT, it is modified. Okay. So CTFT is a major drawback is we cannot find the stability, is it? Then, so next one, so this Laplace transform, it is only Laplace transform by default, it is related to the CT, is it? So similarly for DTFT modification, it is called Z transform. Okay, in Z transform, we are converting time to the Z domain to n. So this is what? So the Z transform, it is a modification. So this is so to overcome the drawback DTFT. What is the drawback? In DTFT, we cannot find the stability. So DTFT, after modification, it is called Z transform. So now in Z transform, we can find the stability. Is it stability? So Laplace transform, it is totally related to the CT. Z transform is totally related to the discrete time, is it? So then next, in next chapter, then in next, we will discuss sampling theorem. Sampling theorem. The sampling theorem is nothing but, already we learned for Fourier series in Fourier transform, Laplace Z transform. So in these techniques, converted time domain to frequency domain. But in sampling theorem, in sampling method, if you apply the sampling concept to the continuous time, it becomes discrete time. If you apply sampling, is it? So the sampling we will discuss in detail in the chapter what is the sampling theorem and why we need to convert continuous time to discrete time. This conversion is different. Time to frequency, this conversion is different. This CT and DT, this CT, DT, two are in it. These two are in the time domain. Is it? Is it? So in sampling theorem, the fundamental, there is only one condition. If you want to convert continuous time to discrete time, we need to follow one condition. That condition is called the sampling rate 1 by Ts. The sampling rate, it must be greater than or equal to 2 times of the fundamental frequency of the continuous time. Is it? This is a sampling rate 1 by Ts, or it is also, we can write sampling rate Rs. Is it? This is sampling rate, it must be greater than or equal to 2fm. Then only we can convert the continuous time to discrete time. So the information we will be discussed in the sampling theorem chapter. Then in the last topic, so we related to the digital signal processing. In digital signal processing, again we are going to learn another technique, that is discrete Fourier series. Discrete Fourier series, it is related to the discrete time. Already for a discrete time we have a discrete time Fourier series. Again for a discrete time, again we are going for the Fourier series. So the major difference is this in DTF is here the x of n has a infinite length. Means for finite length, so the DTF is it cannot be used for the x of n which has finite length. Which has the x of n has finite length. So this is brief story of the signal system. This is a concept. If you learn conceptually, then you can understand the signal system. You can able to answer any question, any fundamental, any difficult questions also. Is it? So this is a very, very important whole concept I have explained here. So step by we will discuss chapter wise from the basics of the signal system, LTA and Fourier series, Fourier transform and Laplace Z transform, everything. And also you should remember, for example in Fourier series what you have learned, the properties are everything. Nearly there are 15 to 16 properties. What are the studied, what are discussed in the Fourier series? 6 times it will be repeated. Same thing, Fourier series properties repeated in CTFS. Whatever you studied in CTFS, same will be discussed in DTFS. Same properties, small little bit difference only. Then whatever properties studied same CTFT, that will be discussed in DTFT. Again some properties again we're discussing Laplace transform, same in Z transform. So number of times we're repeating these properties, then automatically you will get easily, you can easily memorize the properties. That is the major advantage of the signal science system, is it? Then now we are entering into the subject. In the first chapter, basic basic of the signals and systems. First of all, signals. What is a signal? What is a signal? Simple thing. In in, in electronics and telecommunication, you know, time varying any physical quantities which carries the information, that is nothing but signals. Simple. So the magnitude continuously varying with respect to time, and it carries the information. So 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 in electronics, in electronics and telecommunication, so electronics and telecommunication, it refers time varying, time varying. What time varying? What time varying? One is current or voltage and electric field, or magnetic field, and electromagnetic, electromagnetic field. So it carrying the information. So which carries the information. Is it? So it's also signal, it is a function of time. That's simple thing. Just you remember, the signal is nothing but function of the time. So we can write like x of t. So this x of t will be taken on the y-axis, and in y-axis, x of t will be taken on the y-axis, and time will be taken on the x-axis in case of continuous time. But in case of In case of discrete time, this x of n versus time. This time is here, the time it will be denoted by the small n for discrete time. We will discuss what is the major difference between CT and DT. So in x-axis, this is time. In y-axis, x of t. So I'm going to this is the magnitude. So here this x of t, it is called magnitude. Here the magnitude may be, the magnitude may be current or voltage and electric field or magnetic field or electromagnetic field. These are the physical quantities. So these are anything, any one of them continuously varying with respect to time. So this is a basic signal definition. Then in signal representation, so this is a very important. Signal representation. Here the signal can be represented in primarily two ways. One is continuous time, one is continuous time signal. So the signal can be defined one way, that is continuous time signal. The second way is discrete time. Discrete time signal. This continuous time, the magnitude is defined for all values of time. In discrete time, the magnitude is defined for the only integer values of the time. Is it? So this is CT and DT. Already in the explanation of the syllabus, I told you the CT and DT. So here we will discuss what is a continuous time signal and what is the continuous time and what is it discrete time. The first one, so continuous time. continuous time signal. In continuous time signal, already I told you, the magnitude it is defined for all values of time. So for definition, a signal, so which the continuous time signal, a signal that is defined, that is defined, that is defined for all time instants. For all time instants. So it represented as represented as a function of time, a function of time. Here also it is a function of x of t. So example, so what are the examples? You know the sound wave, you know that in sound with respect to the magnitude varies. Is it sound wave? Is it? So now we're going to draw one example. So here I'm taking one exponential decay signal. So in x-axis, the time, you should remember in continuous time, the time you should take t letter. It must be denoted by the small t. In y-axis, this is x of t. Here I am taking one exponential decay signal. Exponential decay. With respect to time, it is decaying. Is it? So these are the time values and the x-axis. Is it? So you can take 1, 2, 3, 4, 5, 6. So coming to the magnitude, 1 unit, 2 unit, 3 units or 4 units. So from this graph, what do you understand? So it has the magnitude not only for 1, 2, 3, 4, 5, and also it has the magnitude for all values. Maybe it has the value for the 1.5, 1.9, 1.99999, 2.0001, 2.5. So magnitude is defined for all values of. So you should remember. So you should write here t it may be fraction plus integer. Okay, fraction and integer. So all, then so you can write all of time. So this is it. The next one, discrete time. So in discrete time, signal. So this discrete time signal, already I told you, it is defined for only integer values of time. So then definition. So a signal that define only at a specific instance, only at specific instance, specific instance. So you should remember that is a integer, is it? So often represented represented often represented as a sequence of values. So you should remember the sequence, it is mainly used for the discrete signal. The term it is used for the continuous. In textbooks or in any examination questions, whenever he uses a sequence, it means it is a discrete time. Whenever he uses signal term, maximum it may be continuous time. So sequence of values. So coming to the example, you know that stock prices, stock market, is it? In stock market, you know, the stock prices, like so so you should remember in discrete time, time must to be denoted by the small n, is it? And the magnitude x of square bracket. So it is called, in continuous time it is called curl bracket. So it defined, so it should have the magnitude for integers only. It doesn't have for fraction of the time, is it? So 1, 2, 3, 4, 5, 6, is it? So integers, the values of time, 1, 2, 3, 4, 5, is it? So here so here it is a magnitude. So here this magnitude, here this magnitude, is it? So these are the magnitudes. So magnitudes. So it must have the magnitude for integer values of the time only. Okay. So there is no magnitude between 1 and 2, there is no magnitude between 2 and 3, and there is no magnitude in 3 to 4, is it? So it doesn't have the magnitude for fraction values of the time. There is a fundamental difference between the continuous time signal and discrete time signal. Always you should remember the magnitude is defined for only integers, is it? So we should write integer. So integer values, integer, is it? Integer. The magnitude may be fraction or integer. It doesn't matter, okay? Just the definition, it is based on only time, okay? You don't take any definition for the magnitude, whether in continuous time, in discrete time, the magnitude, whether it is integer or fraction, anything, it doesn't matter. The definition, continuous time signal and discrete time signal, the definition, it is based on only integer fractions of the time only. It doesn't matter of the magnitude. So this is about signal representation, continuous time signal and discrete time signal. This is a major difference. Okay. Then we go for the periodic signals. Periodic signal. So now, so what is a periodic signal and its characteristics? Periodic signals. So characteristics. So first of all, if you understood characteristic, then you can easily understand what is a periodic signal. So in this, the first characteristic, repetition. Repetition and time period, repetition and time period and frequency. If you understood these three characteristics, then you can understand what is a periodic signal. The second one is very, very important. What is a time period? Time period. The third one is frequency. If you understood these three characteristics, then you will know the periodic signal. So repetition, the signal repeats itself at regular intervals, that is called repetitions. So what happened? The signal itself. The signal repeats itself at regular intervals, regular time intervals, within time intervals. So signal some cycles, repeat something magnitude, some cycle, some structure repeating every time interval, that is called time. The time interval, the time interval between repetitions are two repetitions. So repetitions, the time interval between repetitions. So this time, the gap between two repetitions is nothing but time period. The time period, it is in continuous time, it is denoted by the capital N, capital T, In case of discrete time, it is denoted by the capital M. So these are time period in case of the discrete time signal. So capital T is the time period for in case of continuous time. The frequency, the number of repetition per unit time is nothing but frequency. The number of repetitions per unit time. Here per unit time, here the unit time is nothing but second. Okay, so the unit time is nothing but what? Second. So the number of repetition, number of cycles per second is nothing but frequency. Then the frequency for continuous time is nothing but 1 by capital T. Is it? So this is a general formula. So these are the, then you understood that period signal is nothing but which signal repeats cycles for every time interval. It is a periodic signal. For example, in continuous time, continuous time signal. So for example, I'm taking one signal continuous time. So there is, for example, x of t, x axis in t. This x of t, I'm taking x of t equal to something 5 into sine of 2 pi t. Is it sine 2 pi t, or is it better to take so x of t equal to something Vm sine omega naught into t, sinusoidal signal. So I'm taking sinusoidal signal. Is it? So this is the magnitude Vm. So for observation the signal, you can understand this cycle, it is repeating. This is second cycle, this is a third cycle. Is it? So in negative side also we have same. So same this cycle. So this cycle from here to here, I'm going to here. So find this here to from here. Is it? So this gap, so this interval between these repetitions is called time period. Is it time period? Okay. So time period, the fundamental time period capital T equal to So 2 pi by omega naught. 2 pi by omega naught. Here omega naught. So here this omega naught is angular frequency. Angular frequency. Is it? Here also we can write fundamental frequency omega naught equal to 2 pi by capital T also. Is it? So in case of discrete time, discrete time. So discrete time signal. So in discrete. So already I told you in discrete time, the time must be denoted by the small n, is it? So in magnitude, we should write a square bracket x of n, is it? So here also I am taking this x of n equal to something Vm into sine omega naught into n. So here, so the magnitude sinusoidal signal. There is no magnitude here, here, here. So this is the small magnitude. This is a peak, negative peak. This is zero. Is it? So just observe it. Then you can understand. Again, so now this is second cycle repeating. Middle one, peak value, middle, second lowest one. So this is the peak value. So this is the second highest value. So from the observation, so this from here to here, this is the one cycle. So this is cycle is repeating. Is it? So from here to up to here, the time interval between two repetitions, it is called time period. Capital. So these are the magnitude, peak magnitude. Peak magnitude is V. Peak magnitude, is it? Here the fundamental frequency, so the fundamental time period, so fundamental time period, capital N. Capital N equal to 2 pi by omega naught. So here the concept is, already we have discussed the difference between continuous time and discrete time. Time, it is always integer. Then time period also automatically it must be integer, is it? Time default it is integer, then time period must be integer. Then to make the n integer, so if for example 2 pi, here omega naught equal to 3 pi, then pi gets cancelled, then you will get 2 by 3. n never be fraction value. Never it will be fraction value. It must be integer. So that's why to make the n integer, so we should multiply with the small n. So here this m, it is any integer value, is it? It is what? It is what? Any integer. Any integer. So it is m, it is any integer to make the capital N time period integer. So you can take m from 1, 2, 3, 4, dash, 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 integer. Then, so frequency, angular frequency, the given formula, this omega naught. So this omega naught equal to 2 pi by capital N into m. So omega naught by m, 2 pi by capital N. So it is called fundamental frequency. Fundamental frequency. We will discuss what is a fundamental frequency. I will tell you in the problem. So this is about periodic signals. Okay. So periodic signal we have taken in continuous time signal method and in discrete time representation. We learn how to what is a time period and frequency in continuous and discrete time. Here we have different formulas for finding the time period. In continuous time, we have the formula, this one, time period. But here the formula just extra, what is extra? M is multiplied in case of discrete time signal. Now, just we go for the problems. The first question, a discrete time signal is given by x of n equal to 5 sine 3 pi n. What is the fundamental time period? Is it? So the given signal in the discrete time, it is not continuous. If it is continuous, the formula is different. For discrete time, the fundamental time period formula, so capital N equal to 2 pi by omega naught. Here you should remember this omega naught is not a fundamental frequency. So into m. So this is the omega naught. This is the omega. So from the given in the given question, so 2 pi, so omega naught equal to 3 pi. So into m. So pi gets cancelled. Here we are getting 2 by 3. Then you should take 3. M equal to 3. 3 gets cancelled. That equal to 2. So fundamental time period equal to what? 2. So fundamental frequency, is it? Fundamental frequency that equal to 2 pi by capital N that equal to pi, is it? This is the general angular frequency. This is the fundamental frequency. Okay. So in the question, what is asking? What is the fundamental time period? What we got it? So 2 answer, 2 seconds. So option is 2. But most of the students, they don't know the formula. They use a continuous time formula, that is t equal to simple formula 2 pi by omega naught. Then We will get what is the answer? 2 by 3. But 2 by 3 is not. If it is continuous time, so 2 by 3 seconds, it is the answer. But it is the discrete time signal, 2 seconds. But here the fundamental frequency, what is the fundamental frequency? 5. But 3 pi is not a fundamental frequency, it's a general frequency. Is it? Next question. A discrete time signal is given by x of n equal to 10 cos pi n. What is the fundamental time period? So, in what is the difference compared to the previous question? So here pi is there, but here pi there is no pi. Then we will check it. It's a time period. So from the formula, fundamental time period equal to 2 pi by omega naught. So what is omega naught? 5 only. Is it? Yeah. Okay. So we are getting in denominator, we are getting some 5 value. Then here we can take. So I'm taking m equal to 5. 5 gets cancelled. But here we are getting what? What we are getting? 2 pi. But 2 pi, it is not an integer. It's a fractional number. It is not a integer. It is a fractional number. Then, so 2 pi by 5, it is wrong. 2 pi also wrong. It is also wrong. Actually, so we cannot make the n integer value. It's very difficult. It's not possible. So it cannot be defined. There is no time period. Actually, it is so this discrete time signal, it is not a periodic signal, is it? It is not a periodic signal actually. It is a periodic signal. So there is no fundamental, then it is called a periodic signal. So option is, these are very, very important questions. Okay. The next question. A continuous time signal denoted by the x of t, then what are the units for given signal? Is asking signal units. Already in the second already we have learned the signal is what it may be the magnitude. The signal, it may be current or voltage or electric field or magnetic field or electromagnetic field. These are the physical quantities continuously varies with respect to time. Is it? So that is so that is so the signal units, it may be volts. So these are the ampere per meter. These are the units for the magnetic field intensity. Magnetic field intensity. The formula, general formula, magnetic field intensity, the h bar equal to I by 2 pi r a by cap. So this is a so units. So current units are ampere per r. It's a length. So it's meter. So magnetic field intensity. This is the magnetic field intensity for infinite conductor. Infinite conductor. Whenever infinite conductor carries the current in z-axis, in vertical, so magnetic field will be formed in circular path around the conductor. This is the formula. For semi finite conductor, there is a formula I by 4 pi r. It will be studied in electromagnetic fields. So volt ampere. So this is the units for the electric field. Electric field. Is it electric? You know, formula electric field we can write in terms of voltage, voltage and meter or D, is it? So volt per meter. So it may be volt or ampere meter, it is correct, voltmeter is correct, so all are correct. So answer is all are correct. Yes, next question. A discrete time signal x of n is given the figure. What is the fundamental time period? It's also asking fundamental time period. So here, what is the cycle actually? What is the repetition? What it repeats? So from here to here. Okay. So this is the time period. Is it from here to here? This is repeating. Is it from here and from here to the here? So this is repeating from here to the next repeating. So automatically what we can understand from the observation, 2 pi, is it? So time period may be n equal to 2 pi. Already we know that in discrete time signal time period must be integer. So it is not integer. So it is not pi. It is not 2 pi. So it is also not 44 seconds. So answer, it cannot be defined.